Artificial intelligence is becoming a calculation bottleneck. Most models rely on massive strings of floating point numbers, but a breakthrough architecture called BitNet B1.58 changes the math. By binarizing weights into three states, -1, 0, and +1, it eliminates floating point multiplication entirely. This enables a shift in where AI actually lives. Instead of querying a cloud data center, these ternary models are designed to run locally on the processors inside your phone or laptop. But there is a persistent failure in the data. While this works at massive scales, the performance of models under 1 billion parameters, the exact size needed for mobile hardware, drops off a cliff. The transition to edge AI is stalled by a structural breakdown occurring inside these smaller, highly compressed networks. To find the cause, we have to look at the state researchers have ignored: the zero. In a ternary system, the zero was widely assumed to be a passive side effect, just empty space left over after the important weights were signed as positive or negative. Empirical analysis suggests this assumption is wrong. Measurements of how these models actually process information show a massive discrepancy between what we thought those zeros were doing and their actual impact on the network. It turns out that the total volume of these zeros, the zero-weight mass, directly correlates with whether a 1-bit model succeeds or fails. Solving the small model crisis requires a new perspective on what nothingness represents inside a neural network. Researchers used gradient flow analysis to look past the weights and see how signals actually move through the model during the training process. This chart shows signal intensity. Blue bars represent the 1-bit models. Startlingly, zero-weight positions carry a gradient signal 1.7 times higher than active weights. Across 5 architectures, this constant 1.7x ratio proves zeros aren't empty space. They're the system's most active routing hubs. This discovery revealed a physical floor for AI performance. Models under 850 million parameters fail because they cannot naturally sustain a 10% zero mass. They lack the minimum volume of routing hubs required to move information. Without that 10% threshold, the internal routing network collapses. The model tries to process logic, but it has nowhere to send the signal. This led to the development of GASP, Gradient-Aware Zero Placement. It's an intervention designed to manually fix the zero deficit in smaller models. Instead of letting the model decide, GASP tracks gradient magnitudes everywhere. It finds weak signals and zeroes those positions out, building a more efficient map. This replicates the structure of larger models, protecting high gradient pathways while forcing the rest into a functional, load-bearing architecture. GAS serves as a structural scaffold, engineering the specific zero mass threshold that a small model needs to survive the compression process. However, there is a strict boundary to this technique. If an engineer activates GAS at the very start of training, the model will fail immediately. Early in training, a model's gradients are chaotic and unorganized. Because GAS reacts to those gradients, it ends up in a self-reinforcing loop, deleting connections before the model even knows it needs them. This is the principle of gradient maturity. As shown in this fine-tuning chart, the technique only works once the model has established a stable baseline trajectory. It is a refinement tool, not a foundation. It reminds us that these networks are dynamic structures. Applying a structural fix at the wrong stage of development can be just as damaging as the original problem. This research changes how we evaluate model compression. For years, the metric was, how much does quantization hurt the model? The data suggests we should be asking, how much zero mass has the model accumulated, and is it organized? Understanding the role of zero-weight mass provides a measurable path forward. It offers a way to take the capabilities of massive server racks and fold them into the silicon of mobile devices. By mastering the architecture of what we once thought was empty space, we can finally move AI out of the cloud and into our pockets.